Warm greetings from Anumat Lessons. At the outset, I would like to convey my good wishes and wish each one of you a wonderful and a very happy New Year 2023. May you have a wonderful year ahead and all your dreams come true in this new year. I take this opportunity in thanking all my subscribers for the confidence shown in my channel and for giving me constructive comments wherever possible and encouraging me to move forward. I assure you, in the coming year too, I would be doing the best I can to produce and bring out small videos in topics of mathematics. So, loads of good wishes to all of you from Anu Math Lessons for a wonderful year 2023. This video focuses on the solution of system of equations using LU decomposition. This topic has been chosen based on the request of some of my subscribers. So the agenda of this presentation would go this way, that we would start by understanding what LU decomposition is and use the procedure or the working rule to decompose a matrix, and the concept is further applied to a system of equations in order to solve it using this method. So let's begin by understanding what LU decomposition is. Before we talk about LU decomposition, let us understand what we mean by the word decomposition. Decomposition means breaking down or into smaller parts or splitting. This is the meaning of decomposition. So now we are going to decompose a given matrix into a product of matrices. This is the crux of any decomposition method. But what kind of matrices are used in LU decomposition? Let's see the definition now. So if A is a square matrix, so we are talking about any square matrix, then that can be factored or decomposed into a product of matrices, where which we calling it as LU, and L by the letter talks about a lower triangular matrix and U denotes an upper triangular matrix. As you are all aware, a lower triangular matrix has all the elements above the diagonal as 0. So when I have a matrix, all the elements above the diagonal are 0 is a lower triangular matrix, and all the elements lying below the diagonal are 0 is an upper triangular matrix. So A, the matrix A, can now be written as a product of the two matrices. One is a lower triangular and another is an upper triangular matrix, and hence the decomposition is called the LU decomposition. So let us see now what is the procedure in order to split this into the product of these two matrices. So the working rule is explained here. I first write the given matrix as I into A, where I is the identity matrix having the same order as that of A. So suppose I give for an example, it is 1 0 0, a 3 by 3 matrix, 0 0 1, and we are given a matrix of some form, say 4 0 1, etc., etc. Let's not write any of these values. This is the first step that I do, is replace the given matrix A in the form of I times A. Then my aim is to reduce this right hand side matrix A into an upper triangular matrix and thereby make some changes in I so that this becomes a lower triangular matrix. So that's my aim. I apply Gauss elimination method and reduce this right hand side A into an upper triangular matrix. I'm sure all are aware that Gauss elimination method, we apply row transformations. There are elementary row transformations which can be applied, where I can actually rewrite or multiply a particular row by a non-zero constant where k is non-zero, and then I could also rewrite Ri, the ith row, to be Ri, the ith row values plus some k times the jth row values. This could also be done. And there is the another operation where I can swap or interchange any two rows. Now, one of the limitations of LU decomposition, before I continue, is that row interchanges will not yield the method or the result that we are looking for. That needs a different technique to tackle. So in this particular video, when I'm talking about reducing a matrix by Gauss elimination, using row operations, we are only focusing on these two operations and not on row interchanges. So when we want to interchange any two rows, the concept is slightly different, which I shall bring out in my next video. So when I remove this particular part where I am not talking about row interchanges and focusing only on these two operations, let's go back to A equal to IA now. So I write Ri, or first row. My first element has to be 1. The pivot element has to be 1, whereas here it is 4. So what am I going to do? I divide by 4 and the entire row by 4, so that this first element will become 1. Second, 0 by 4 is 0. Third element is 1 by 4, because I am dividing that element, that whole row, by 4. Anyway, in detail, we shall see an example in the next slide. What I am stressing to say here is, when the process of reducing this matrix A into an upper triangular matrix, we cannot keep I as it is. We need to make some correction there. So what we do is, whichever element is being eliminated by using the row operations in A, whichever element is eliminated, we copy that element in I in the corresponding or the matching position. What I mean by that is, let's look at this first operation. Here I have eliminated 4. I have made it 1. Now which position is this? 1, 1 position. So what am I going to do is, I am going to copy that 4 in that 1, 1 position in I. So this will further now become 4 and not remain as 1. So whatever operation we are doing in A, correspondingly, elements which are eliminated will be copied to the matching element. When I say matching, we are ensuring the position is the same. If it is 1, 1 position, it is 1, 1 position. If it is 2, 2 position, it will be 2, 2 position. If it is 2, 3, 1 position, it will be 3, 1 position. So corresponding positions it will change. Thereby, I will reduce to a lower triangular matrix and A will it reduce to an upper triangular matrix, and thereby the matrix A can be written as the product of L and U. So this is the crux or the method or the working rule for reducing a square matrix into the LU form. Let us apply this procedure in a problem in my next slide. Let's take up an example here, which is a 4 by 4 matrix, as it is shown here to you. So this is a 4 by 4 matrix, and my first step, as it says, is I equal to IA, where I is an identity matrix of order 4. So I rewrite it in this manner. And now my aim is to change this and or reduce it into an upper triangular matrix, and the method that I am applying is Gauss elimination method. So let's quickly revise what this method is. So what we do in Gauss elimination, taking the matrix to be a 4 by 4 one, is we make the first element, the leading element, diagonal element, to be 1, and then using row operations we are making all the elements below it 0. Then make the next diagonal element 1 and make all the elements below it 0. Make the next diagonal element 1. Making use of it, make the elements below it 0. And then final diagonal element 1. Kindly note that we are not applying or using the interchange of rows in this particular video, as this cannot yield the result that we want. And thereby what is the next step in this process of reduction, reducing it into an upper triangular matrix? We have to make the corresponding changes in the identity matrix so that this reduces into a lower triangular matrix. So let's see the procedure that we just discussed before in the previous slide. Let us apply it and see how it works here. So we have first written it in the form of A equal to IA, and then we see that the leading element here is already 1, and here also it is 1. So there is no big change, so it continues to remain as 1. Now the next step would be to make all the elements below the leading diagonal 1, which is to be 0. That is these three elements, 2, 3, minus 1. We should make them zeros using the leading element 1. So what is the operations? Obviously would be R2 is R2 minus 2R1, R3 is R3 minus 3R1, and R4 that you have is R4 plus R1. So we are making use of these three operations in order to reduce these three positions as 0. Now what is happening when I make them zeros? This 2 is now going to occupy the position as 2, 1 position in I. 3 occupies the position 3, 1 position in I, and minus 1 is copied in the 4, 1 position in I. And these three now will become zeros here. Automatically the other elements change. So let's see the refined matrix. It is this. So we see that the matrix here A, this 2, 3, minus 1 is carried forward in these elements here. 1 remains 1, and here it is zeros. The remaining elements correspondingly using the operations change. Now what is happening? We have completed with the first column. Let's go to the next column. We have the next diagonal element to be minus 1. It has to be 1, and therefore the operation would be, let's multiply the second row by minus 1 so that it will give you 1, and thereby what is the operation that we are doing? What will minus 1 shift to? Minus 1 will shift to the 2, 2 position in I. So let's look at the refined matrix. Now you see this is what happens. So minus 1 is occupied here as we expected, and this is becoming 1 as we wanted with the remaining changes in that row. Now we have minus 4, 3, that is the element below the second diagonal element, to be made zeros, making use of the second diagonal element, which is 1. So obviously the operation would be R3 is R3 plus 4R2, and R4 is R4 minus 3R2. And so that minus 4 will get shifted to the 3, 2 position, and 3 will be getting shifted to the 4, 2 position. So let's see what is happening to the matrix. So you see 4, 3 has jumped up here, and these two have become zeros here. So 1, 0, 0, 0, again 1, 0, 0. Now let's move to the next diagonal element. What's the next diagonal element here? 3. So I need to make it 1. So obviously I need to divide the third row by 3. So what is happening thereby? 3 is getting eliminated and is pushed to I. So which position? So 3 is getting shifted to this position where there is 1, and thereby the changes are made in A. So let's see what's happening. So you see 3 has come up here. Yes, as expected, and here it is 1. So we have got it correctly. Now below that 1, there's already a 0, so there's nothing to change. So we have no problem there. Go to the next diagonal element, it's minus 13. So I will divide by minus 13, so it becomes 1. And now see what is the final matrix that I have. So you see 1, 1, 1, 1 along the diagonal. All the elements below the diagonal are 0. So this is automatically U, the upper triangular matrix. See how it is changed here, because minus 13 has been eliminated. Minus 13 is occupying the 4, 4 position. So you got it here. So, and if you see all the elements above the diagonal are zeros. So this is the lower triangular matrix. So thereby we have now constructed the matrix A, or split the matrix or decompose the matrix into a product of the lower triangular matrix and the upper triangular matrix, and therefore A is equal to L times U. So the decomposition of the matrix is done. successfully. I hope the procedure has been clear. Many more problems could be attempted in the same manner. Even though the order is higher, this could be done in a very easy and a simple fashion. Let's now look at an example where we solve a system of equations. I will carry the same matrix there as the decomposition is already being done. So let's see that particular problem in the next slide. Hoping that the procedure explained in the previous slide was comfortable and understandable, let us proceed by applying the same technique in solving a system of equations. I have chosen a system of 4 equations and 4 unknowns, bearing coefficients exactly the same as what we did in the previous problem, so that the decomposed matrix could be taken up as it is. So if you look at the coefficients here, it is 1, 1, 0, 3. This is 1, 1. There is no x3 and then you have 3. So it's 1, 1, 0, 3, 2, 1, minus 1, 1 as you can see here. 2, 1, minus 1, 1, 3, minus 1, minus 1, 2, minus 1, 2, 3, minus 1. So this is the exact matrix which we took up in the previous slide to decompose it. So I have taken the same coefficients so that we could use the decomposed matrix. Any system of equations can be solved provided we are able to write it in the standard matrix form. So we shall express it in the matrix form, writing it as Ax equal to B, where A is the coefficient matrix, S is the matrix of unknowns, and B is the matrix of constants. So A is the coefficient matrix. If you recall now, it's same as what we did in the previous slide. X is the matrix of unknowns, x1 to x4, and B is the constant matrix which has all the right hand side values in it. So now instead of writing down a different procedure, we are now using the LU decomposition technique. So that means we have now learned how to rewrite a given matrix of the form L into U. So in place of A, I could replace it by L into U, so that Ax equal to B can be now rewritten of the form LU into X is equal to B. So I have just replaced A by LU because I am using the decomposition. Now L is a matrix, U is a matrix, X is a matrix, and we know that product of matrices satisfies the associative law. So we could rewrite this as L into UX is equal to B. So I have just changed the brackets from LU to UX. That's it. So L into UX is equal to B is the equation that we get in the matrix form now. So suppose I called such UX to be equal to some Y. So now this equation now turns out to be L into Y into B. So now L is the lower triangular matrix which we already have found using the decomposition technique. Y is a new set of unknowns. So new set of unknowns, we are calling it as Y1 to Y4. And then B is the matrix of unknowns which is already known to us. So L is known, Y is to be found, and B is known. So what is happening? The equation Ax equal to B, is now transformed to, you're having Ly equal to B, and so that when I substitute that Y, and what is Y here? Y is equal to Ux. So I'm splitting it into two systems here. So Ax equal to B is now written as Ly equal to B, where Y is equal to Ux. But what is my actual unknown? My actual unknown is X. So I start with, so where do I start? Do I start with this system or this system? So I start with Ly equal to B. So that's very important. We should know first what should we solve. We first solve Ly equal to B because we know what is L. We want to know what is Y. B is already known. So I solve Ly equal to B, get the values of Y1, Y2, Y3, Y4, and then use them in Y equal to Ux. So Y is now known. U is already known because of the decomposition, and X is to be found. X is what? X1, X2, X3, X4. So I first start by solving Ly equal to B, and then substitute that answer y in this system of equations, writing it as y equal to ux, and thereby solve for x. Let's do this elaborately in my next slide. Continuing with the solution, let's first start writing the decomposition as we did in our previous slides for A. So A is decomposed into, this is L and this is U. Now, as we said in our earlier previous slide, we are going to first start by solving L into Y is equal to B. This is our first step to find out the values of Y. So how do we write that system? L into Y, this is L because this is the lower triangular, this is Y, and this is equal to B. So here, since this is a lower triangular, I use the forward substitution. See, 1 into y1 will give you equal to 8. The second equation will give you 2y1 minus y2 equal to 7. So we are using forward substitution in order to write the four equations. So there is no big solving here. So y1 equal to 8 is the first equation. The second equation is 2 into y1 minus y2 equal to 7. The third equation is 3y1 minus 4y2 plus 3y3 is equal to 14. The fourth equation is minus y1 plus 3y2 minus 13y4 equal to minus 7. So from here you automatically get y1. I substitute y1 here to get y2. I substitute y1 and y2 to get y3. And I substitute here to get y4 directly. So the solution is directly obtained for y in this manner. So now that I have solved Ly equal to B to get y1 values as y1, y2, y3, y4, what is my next step to solve? The next step is to solve y equal to ux. So u here is my upper triangular matrix is this according to the decomposition. So I write that x means x1 to x4 and y are the values that I have just now found. I carry that here, and since it is here an upper triangular matrix, I use the backward substitution. Now look at the first equation from the back. If I write 1 into x4 is equal to 2. So let me write it that way. Then the next equation is 1 into x3. So x3 plus 13 by 3 into x4 is equal to 26 by 3. Then x2 then plus x2 plus x3 plus 5 into x4 is equal to 9. That's my next equation. X1 plus x2 plus 3x4 equal to 8 is my final equation. So I directly get x4. I substitute x4 in this and get x3. And then that will give you 26 by 3 minus 26 by 3, which is equal to 0. I substitute the value of x4 and x3 in x2 and get the value minus 1. I substitute x2 and x4 and get the value of x1 to be 3. So we are using forward substitution in order to get the values of y. So I am using forward substitution here because I have a lower triangular matrix, and here I am using the for backward substitution and to get the values of x. So I get the values of x4, then x3, then x2 and then x1, and finally conclude the solution for x is to be 3 minus 1, 0, 2. It could be checked by substituting in all the four equations and we find that it satisfies perfectly, and that's the solution, and we have applied the LU decomposition in order to get the solution. There are a number of techniques, no doubt, but the LU decomposition, because we are breaking the matrix into a product of L and U, so first we solve Ly equal to B, get the values of y, then use that y and write y equal to ux and get the values of x. That's the procedure which we follow in order to solve this system of equations. So this short video has focused on defining what LU decomposition is, and then we moved on to apply it to decompose a square matrix and use that square matrix in the system of equations in order to solve it. So this is what this video focused on. As I said, the limitation of LU decomposition is the absence of the usage of interchange of rows, which has the concept of permutation matrix to be included. I shall do that in my next video, and with examples there too. So I hope this video and this concept has been understood and is clear. In case of any doubts, you can please feel free to post in the comment box. To the best I can, I shall answer you. Thank you for your patience and thank you for your time. So see you. Good wishes. Once again, a very happy new year to all of you. Goodbye.